Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is the enthalpy of formation and reaction, and the section in the textbook is 15.3. Here are the learning outcomes. At the end of this video, we'll review the different forms of energy, and in particular, we're going to be focusing on chemical energy. You'll know the concept of the enthalpy of reaction. You'll understand what the enthalpy of formation is. You'll understand how higher heating value and lower heating values relate to the enthalpy of reaction, and you'll be able to calculate the enthalpy of reaction for our combustion process. So first, let's go ahead and review forms of energy, and in particular, we want to focus on chemical energy. Here's a picture from the book, and it's actually pretty nice, in that we're looking at a molecule here, which has two different atoms on it, or two molecules, sorry, each made of 3 atoms, and they're pointing out the different forms that energy can be in. So for example, we can have nuclear energy, which is holding the intramolecular particles together. Then there's the chemical energy, which is holding the atoms together. There's the latent energy, which holds 2 molecules together. And then we have sensible energy, which is represented by rotations and vibrations of this chemical bond that I have right here. And so the energy associated with these 2 molecules together is a summation of all these different types of energy. Remember, if we've got a gas, we don't have much energy that's holding these 2 latent parts together, whereas if it's a liquid, they're held closer together. Now, what we're looking at now is going to be changes in the chemical energy, because we're going to be changing these molecules from one molecule to another. So in essence, this chemical energy that's associated with this big red circle here is being broken. And so we're going to be quantifying what that chemical energy is. Now, one point I have with this diagram here is it makes it look like energy is released when the bond is broken. It's actually the opposite. It actually takes energy to break a bond, but that's sort of a subtlety we won't worry about right now. So now when we're doing our energy balances, we're going to need to consider 2 different things. We're going to be considering the change in energy of the state and the change in energy of the chemistry. Now the state is, we've done this for most of the semester so far and most of the basic thermodynamics. That's things such as the pressure and temperature quantify the energy of the state, and that's what we mean by state. But now we're going to be looking at the chemistry, because we're going to be taking one molecule and turning it into a different molecule, which means we're going to be changing this chemical bond. So let's talk about what is the enthalpy of reaction. And so the enthalpy of reaction is associated with the breaking and formation of bonds. And so this diagram here shows the reaction of a methane molecule, so we have CH4 here, reacting with 2 O2 molecules, right? And so I've kind of shown it with bonds, because what happens in order for this reaction to go forward, and so I want to go ahead and form a complete combustion process, which is going to give me 2 H2Os, which I've shown here, and a CO2. Now notice the elements balance. I've got 4 green dots, and I have 4 red dots, and I have 1 blue dot. However, the bonds are in different locations. And so when a reaction occurs, what has to happen is these 4 bonds here need to get broken, and that takes some energy. And those 2 bonds need to get broken, and that takes some energy. So there's actually energy that goes in to breaking all of those bonds. And you can imagine, it's just like the analogy of if I had 2 things tied together and I ripped them apart, it would take energy. But then what happens is I form bonds, and so these bonds are formed and they actually give off energy. And so I've got those 4 bonds being formed, and then these 2 double bonds for the CO2 being formed right there. And so the enthalpy of reaction is going to be the difference between the energy I have to put in to break the bonds minus the energy given off when I go ahead and form the bond. And so when we talk about the enthalpy of reaction, so the book uses the symbol H sub R, and these are combustion processes, so it also uses the symbol H sub C. They're the same thing. And what we're looking at is the enthalpy of the products minus the enthalpy of the reactants, right? And so that's just the way it's done with products minus reactants, sort of like out minus in kind of idea. So the products are over here. And so as I form bonds, and so if I form very strong bonds, that enthalpy drops down pretty far because it's given off the energy. If I break bonds, then the enthalpy goes up. And so what you can realize is that exothermic reactions, those that give off a lot of energy when they form the bonds, the net enthalpy of the products is going to be less than the enthalpy of the reactants, because it's given off a lot of energy. In an exothermic reaction, it's the opposite. The enthalpy of the products would be greater than the enthalpy of the reactants. In the rest of this video, we're going to be looking at how to go ahead and quantify what the enthalpy of these particular components are. So first thing we need to do is discuss this concept of the enthalpy of formation. And this is best kind of done by just looking at an example here where what I'm going to do is I'm going to take methane and oxygen, all right, and I'm going to go ahead and combust it, and then I'm going to form CO2 and water. And let's say these come in at 25 degrees Celsius, and after they burn, they give off some heat, so we'll give off some heat Q, such that the products come off at 25 degrees Celsius as well. All right. Now, if we look at our energy balance, we've got a steady state system here. Means the change in energy of this box is going to be 0. I'm going to look at the rate that energy goes in, and then I'm going to go ahead and look at the rate that energy goes out, and those things have to be equal, right? And for each one of these energies now, since I'm taking molecules that have different identities in the in and the out, I'm going to have to be adding the energy of the state and the energy of the chemistry for each one of those components. Now, the energy of the state, for example, is pressures and temperatures. And so, since this is at 25 degrees C and 25 degrees C, those terms are actually going to be 0 because it's not changing. So all I need to do is look at the change in the energy of the chemistry. However, this term right over here isn't going to be 0 when I add up the products and the reactants differently. In fact, I know it doesn't have to because I've got to look at, be able to calculate a positive value of Q. We know that heat is going to be given off. And so what I'm going to be looking at is the energy of the chemistry of the CH4. I'm going to be adding it to the energy of the chemistry of the O2, right? And then I'm going to be subtracting the energy of the CO2, and I'm going to be subtracting the energy of the H2O. And the differences between those is going to give me this value of Q. So I need to determine what is the energy of CO2, the absolute enthalpy, essentially, or the absolute enthalpy of an oxygen molecule. And that's the idea of the enthalpy of formation. So let's go back to, here's our little diagram here. And so if I'm looking at just this molecule, the one in the upper left, for example, and I don't know what the enthalpy of formation is, I need to know how much energy did it take to go ahead and form it. And in order to do that, I need some sort of reference point. And so here's the reference point that I'm going to use, right? And this is the convention. We say the enthalpy of formation of these components right here is 0. That's just being defined. So pure carbon, H2, N2, and O2 all have an enthalpy of formation of 0. And so the notation we use is H sub F for enthalpy of formation. And this degree symbol up here means it's at the standard state, which means that it's at 25 degrees Celsius, which is room temperature, or 77 degrees Fahrenheit. So that's what that little degree symbol right there means, is that it's at the standard state. It also means that it's 1 atmospheric pressure. So then, what I'm going to do is, if I want to calculate the enthalpy of formation, for example, of CO2, what I need to do is that I'd say, well, what's the enthalpy of formation of my products minus my reactants? Well, the enthalpy of formation of the O2, we just said, is 0, and the enthalpy of C is 0. And so that value right over there is going to be 0. And then this right over here is going to be giving off energy. And so what I'm going to have is 0 minus the energy associated with those 2 double bonds. And that number right there is going to be less than 0. So that tells me that the enthalpy of formation of CO2 is going to be some negative value. So it might be down here on my diagram, HF of CO2. Right? Now, if instead I was to maybe look at the enthalpy of formation of a hydroxyl, which is what this OH is over here, this is a hydroxyl. Again, now I've got the enthalpy of those two, which is 0, right? But now what is going to have to happen is I've got to break those, and then I'm going to go ahead and form this. And an HH bond plus an OO bond is not the same as 2 OH bonds, and it turns out that this actually takes energy, and so my enthalpy of formation of hydroxyl is actually up there at some sort of positive value. Well, you don't have to calculate those for your own. There's a table of them. And so here I show the beginning of table A26, which is the enthalpy of formation values. And first of all, you see these top 4 here, carbon, hydrogen, nitrogen, and oxygen. And they're the diatomic versions of it. Their enthalpy of formation here is 0. Note that the units are kilojoules per kilomole, and that's pretty helpful because when we balance our equations, we tend to do it in moles. And then you see the enthalpy of formation, these first few, carbon monoxide, carbon dioxide, water vapor, things that tend to be products of combustion, and we realize that their enthalpy of formation is negative, and that's because it's an exothermic reaction if I go ahead and form those products from these reactants here. I briefly want to go ahead and discuss heating values, because heating values are related to the enthalpies of reaction. So this is table A27, and what this is just some properties of some fuels, and then there's this value, these last two tables, which is the last two columns, which is the higher heating value, often written as HHV, and the lower heating value, which is written as LHV. And so those values right there are the amount of heat that is given off if I was to go ahead and burn this particular fuel with complete combustion, stoichiometric air, and then bring it back down to 25 degrees Celsius. So the higher heating value is the enthalpy of reaction, or the enthalpy of combustion, and these are always reported as positive values, so it's probably a little better to say the absolute value of that, because for exothermic reactions, these values, H of R, is actually less than 0. And what I'm going to do is I'm going to take the summation of the mass times the enthalpy of all the products that I form, subtract the mass and the enthalpy of all the reactants that I form, and the difference between that's the higher heating value. And again, I'm going to be taking the absolute value of it, because we tend to talk about those as a positive value. All the values in this table are positive. Right? So what is the enthalpy? What are each one of these H sub I values? Well, those are going to be the enthalpy of formation for each one of the components, because we're doing all this at standard state, 25 degrees Celsius, 77 degrees Fahrenheit, and that's that little degree symbol means. And that gives me the higher heating value. And this is a kind of a nice number, because it tells me essentially how much heat is given off, or energy is released when I burn something. So here again, I show that if I was to do this for CH4, I'm going to go ahead and take my difference between, here I've written it, so the absolute value, I switched it around, the enthalpy of the reactants minus the enthalpy of the products to give myself there a value that's going to be greater than 0. And so I've got my CH4 and my O2, formed CO2 and H2O. And I need to determine the relative mass of each of those. If you look at these units, they're kilojoules per kilogram. So if we compute it per mole basis, we just need to use the molecular weight to get it per kilogram. All right. So as an example, let's go ahead and calculate what the lower heating value of propane is. So first we need to balance our equation for propane with stoichiometric air. So propane is C3H8. And the chemical formulas are all given in table A1. You don't need to memorize those. Plus, and now we've got our air, O2 plus 3.76 N2. And complete combustion is going to go ahead and form CO2 plus H2O plus nitrogen. And then we'll go ahead and balance that equation. I have 3 carbons on the left, gives me 3 carbons on the right. I have 8 hydrogens on the left. That's going to give me 4 water molecules over here on the right. And now I can go ahead and balance my oxygens. And so I have 3 O2s and I have 2 O2s. That gives me a 5 in front of that air. And so then 5 times 3.76 is about 18.8. So there's my balanced chemical equation with stoichiometric air. And so now what I want to do is determine what the lower heating value is. Well, I'm going to be finding the enthalpy of a reaction. I'm going to be doing all of that at standard state, which means this left-hand side comes in at 25 degrees Celsius. The right-hand side is at 25 degrees Celsius. And so I'm going to be taking the products minus the reactants, so the enthalpy of the products minus the enthalpy of the reactants. And I'm going to be determining what that value is right there. And that's going to be the lower heating value. Right? And I should mention the difference between the lower heating value and the higher heating value is simply a matter of whether this water right over here comes off as a liquid or as a vapor. And so if it comes off as a vapor, this would be the lower heating value, and that's usually the more common number that you run into, because water, after a combustion process, tends to be released as a vapor. It may condense after it leaves the stack, but normally it's a water vapor. So what we're going to do now is we're going to find all the enthalpy of formation, because all these enthalpy values here are just the enthalpy of formation for each one of these components. So if we go back to our enthalpy of formation tables, we can see here I've got it for carbon dioxide of minus 393,520, and I'm going to need water vapor, my 241,820. I'm also going to need it for propane. It's a little farther down on the table. So let's go through and put in those numbers right there. So I've got 3 moles of CO2, and I have a minus 393,520. That's the enthalpy of formation of CO2. And then what I need to do is add the 4 moles of water. That is minus 241,820. And so since I've got this nitrogen at 25 and this nitrogen at 25, those values are going to cancel out. I won't even bother putting those in there. And so then I'm going to subtract the reactants. My reactants I had -5 for the oxygen, and that enthalpy of formation is 0. And then I need to go ahead and subtract, and this is going to be the enthalpy of formation of propane, which is -103,850. All right, so now what I'm going to do is I'm going to go ahead and add these up together. And so I'm going to find out what the total value is, and I find out that that is 2,044,000 about. And those units of that are kilojoules per kilomole of C3H8. So if I went in terms of kilograms, what I need to do, divide that by the molecular weight, and it's the molecular weight of propane, which is 44 kilograms per kilomole. That will give me kilojoules per kilogram, and that number is 46,464. And the units on that are kilojoules per kilogram. And you can go back and compare that with the table in the back of the book we were just looking at. You find that's pretty much what the lower heating value is for propane. And again, the lower heating value because we had the water leaving as a vapor instead of a liquid.